Hello and welcome! In this video, I'm going to briefly be talking about what a moment is and how to calculate it. Now, I have a very basic example here to start off with because I'm going to talk about the kind of theory behind it before we get into the actual math. The way I kind of think about a moment is the quantification of a force causing something to spin. So if you think back to physics or even just forces in general, whenever you calculate a force, it's understood that that force is causing movement, translationally or otherwise. And we don't think about the things spinning because of this force. We just know that the force is moving something from here to here. A moment is saying that, hey, maybe this whole thing right here is moving down like this. That whole thing is moving downward. Maybe that's happening. But the fact that this force, that 15 newtons, is not centered, it's going to make this thing move almost like this. And that quantification of its spinning is what a moment is. And we can calculate it pretty easily. The formula for a moment, or a torque even, same thing, depending on what your discipline is a force times the distance. And unlike forces, a moment is subjective almost. Your moment that you calculate is entirely dependent on a point of reference. So if I were to take the moment about point A, for this formula to work, I would do the distance between the force and point A, which is 8 meters, multiplied by the force itself, which is 15 newtons. And that is 120 Newton meters. Newton meters. Now, that number is based on point A, the moment generated by the force with respect to point A. Now, let's say, I'm going to slide up. I want to find the moment about point B, because a moment is subjective. We use the same formula, but in this case, our distance is different. Our force is acting on point B, which means the distance between the point and the force is 0 meters, which means that no moment is generated. And this goes back to a moment is the quantification of something spinning, and nothing's spinning. This force is not causing point B to spin, it's causing the thing to spin around point A. And by the thing, I mean this bar, AB. Now that's what a moment is in its most basic application. In practice, your moments are going to be a little more complicated than this, and depending on what you are studying, you could go into 3D. This is a slightly different application. So let's say your force is applied diagonally. So this is still 15 newtons, but now it's applied at a 45-degree angle. That formula that I had written down, m equals force times distance, we still use this formula. The thing that we need to look out for, though, is this d, this distance. Whenever you're calculating a moment, you want the distance perpendicular to the line of action of the force. And the line of action of a force is its trajectory or path for infinity in both directions. That is its line of action. And we want the perpendicular distance between our point of interest. Is this distance here. This distance right here. This is D. Use a different color. That distance is D. Now we can either calculate that distance, or we brush off our physics knowledge and break this applied force into components. And the components of a force are the projections, in a sense, onto an axis. And if you don't know what that means, that's no big deal. Basically, a component is the amount of our diagonal force that is working in one direction. So this I'm going to call Fy, and this I'm going to call Fx. In 2D, this is pretty easy to calculate because it's just simple trig. Our two components are based off of the xy coordinate plane, which means they meet and make a right triangle. So we can turn this 15 Newton force into a right triangle, where this leg is Fy and this leg is Fx. And then we just do trig to calculate those values. So using trig, I can calculate Fy to be 15 times the sine of 45 degrees. And this comes from SOHCAHTOA, opposite, or this. 15 is our hypotenuse. Our side that we care about is opposite to our known angle, so we use SO, or the sine. And then we use the same logic to calculate Fx. 15 cosine of 45 degrees. And these forces that we just calculated, those are the forces that you'll plug into this moment equation. And they each have their own distance from point A. So Fy, its distance is 8 meters away from A. Fx runs into A, so its distance is 0, which means the moment generated by this applied force is 15 times the sine of 45 degrees times 8 meters, which is 84.85 Newton meters. Now, if we wanted to figure out this perpendicular distance, we would just set up a quick equality. And this is, you most likely won't have to do this in a question in class, but it's important to know. Helps you get comfortable with the material. So we know that the force, or the moment generated by the force, the 15 Newton force, is 15 newtons times some distance from A. And this equals 84.85 Newton meters, because this moment is equivalent regardless of where this force is pointing, because we've accounted for the fact that it's at an angle by using the component. And we can do some quick algebra here. Figure out that that distance is 5.65 meters. So if we were to solve this using 15 newtons in this distance, we would end up with the same moment, and that's how we know that it's correct. Now this video was a little on the short side, but I wanted to kind of go over just what a moment is in its most basic form, and then in another video we'll go into more complicated moments and a combination of forces acting on one object. So the most important takeaway here is that moments always exist when you're dealing with an object and not a point on a graph like you probably did in physics, at least for the first part of physics. I hope this helped you some. Feel free to leave a comment if you have another topic you want me to cover, and happy learning!